Okay, ladies and gentlemen, it's an honor for me to close this session, and especially following a paper by Professor Yukitaka Murakami in Japan. It's a real honor. Next week in Salamanca, in the Zamora Technological Campus, we have the Spanish Conference on Fracture International Edition and an EC10 workshop on environmental assisted cracking and hydrogen embrittlement. Murakami finally could not attend to give a plenary lecture, but we have plenty of Japanese professors, some of them working with Murakami. For instance, Professor Ryuichiro Ebara from Fukuoka University, Professor Masahiro Endo, Fukuoka University, Masahiro Goto, Oita University, Masao Sakane, who will be attending the next workshop on multi-axial fatigue and fracture, and Kenichi Takai from Sophia University, a real expert in electrochemistry, also working with Murakami. And in addition, the younger Professor Akihide Saimoto from Nagasaki University. In addition, here we have some keynote and invited lecturers from Russia and Italy. For instance, Professor Giovanni Meneghetti, who is present here, and Professor Valeris Dianico. I wonder if he is visiting Urbino, but he's in this conference. And another paper by Philippe Marbier. I think Valeris is not here.
No, it will be.
It will be, but yeah, he will be in Zamora. Okay, let's go to the presentation. I think the counter is running. That's too problematic. I try to be short. The title of the presentation is... I come the name of Valerie is not here. It's not crack defense and mixed mode fracture behavior of progressively down paralytic steel. My co-authors are the organizers of the conference, Beatriz González and Juan Carlos Matos. They are working very hard now in Zamora. I shouldn't be here, should be in Zamora, but I am working very hard online, up to 3 a.m. and 4 a.m. Very hard work. I am going to divide my presentation into 5 parts: introduction, experimental procedure, experimental results, discussion, and conclusion. I missed the pointer, but let's go. First part, the introduction, we expected, not the first part. And the end of the work is to study the influence of cold drawing process, the cold drawing process on the fracture behavior of paralytic steels. This process of manufacturing inducing heavy plastic strains in the steel just to increase its resistance. The experimental procedure, chemical composition. This is a quasi-eutectoid steel with, roughly speaking, 0.80% of carbon and other chemical components, and the base material is a hot rolled bar, not cold drawn at all. And after several steps or stages of cold drawing, we obtain a heavily drawn material after 6 drawing steps. Cold drawn steel, commercial prestation steels, after 7 steps of drawing with a cumulative plastic strain of 1.1. Now the experimental procedure, we use samples as cylindrical bars of 300 mm length. This is the universal testing machine for fracture mechanics analysis. The testing, we pre-crack by fatigue, tensile fatigue with sinusoidal wave under load control and decreasing load in steps. Typical frequency of 10 Hz and error ratio equal to 0. No overload, no. We don't believe in plasticity crack closure, as you know, but we discussed in Malaga heavily. This topic was heavily discussed, and I propose in 2 years organize. Luca had the same idea, 2 parallel sessions, believers and non-believers. And so like probably George Grinka will be here in 2 years. Fracture, monotonic tensile loading under displacement control up to final fracture, 3 mm per minute crosshead speed. A typical fracture mechanic test. This is not a standard fracture mechanic test because they are thin wires, and an extensometer was placed in front of the crack mouth in such a manner that the load displacement curve FU was recorded. And now we have the records after this experimental test. We have the experimental results, but let me explain first about the microstructural evolution. The steel is called B0123. The number of drawing steps undergone by each steels, 4, 5, 6, and 7 drawing steps, the heavily drawn commercial pre-stressing steel. And with regard to the cross-sectional area and transverse section, no effect of cold drawing could be observed. Only an increase of packing closeness with decrease of interlamellar spacing, but no orientation. Both perlitic colonies, the set of lamella equally oriented, and perlitic lamella, ferrite cementite lamella, are randomly oriented in the transverse section. But with regard to the longitudinal section, we have a clear evolution towards a markedly oriented microstructure, a quasi-fiber reinforced material. This is a microstructure like a composite material, heavily drawn, and we have a clear progressive evolution, geometrical evolution of the two microstructural levels, both perlitic colonies and perlitic ferrite cementite lamella, and we have an increase, a progressive orientation of the colonies, and progressive slenderizing. They become more slender in the drawing direction, and with regard to the lamella, they also are progressively oriented quasi-parallel to the drawing direction, or y-axis in the final stages of drawing, and there is a decrease of perlite interlamellar spacing, which means an increase of packing closeness, as in the case of the transverse section. But in this case, we have the clear orientation. It is a heavily oriented material, a markedly oriented material in the drawing direction of y-axis, with consequences in fracture. Here we have evaluated the perlite lamella angle, microscopic angle theta m, measured in relation to the cross-section of the Y. It increases with plastic strain, and it increases with cold drawing. With this imposed plastic strain, heavily drawn steel, it increases the angle of orientation in relation to the transverse direction. Here the appearance of fracture surface with the evolution progressively down drawn steel, hot roll material, not drawn at all, mode 1 fracture, purely isotropic, slightly anisotropic in the first stage of drawing, but roughly speaking it still breaks in mode 1. Roughly speaking, it is still isotropic, and from 4 steps of cold drawing to 7 steps of cold drawing, we have a progressive effect, progressive anisotropic effect with cracked embryos, cracked branches, cracked deflections, and a very stepped fracture appearance, very rough because of the anisotropic effect, because of the microstructural orientation. In heavily drawn steels, the fracture is very anisotropic with abundant deflections and longitudinal cracking. Longitudinal splitting or delamination between two similar microstructural levels, either the colonies or lamella itself. Here we have the profiles, quasi-isotropic behavior up to step 3 of drawing with increase of roughness, and the anisotropic deflection effect appear from B4, 4 steps of drawing, clear in B5, more pronounced in B6, and very marked in B7 with a very steady fracture surface and a crack deflection angle, microscopic angle, reaching almost 90 degrees, quasi-parallel to the drawing direction or y-axis. As the number of drawing steps increases, so does the crack deflection angle, the microscopic angle. We spoke about the microscopic micro angle in the previous slides, and the roughness of the fracture surface as a consequence of the manufacturing process. Here we have the profile in schematics, the fatigue. An interesting question is, why does fatigue propagate in mode 1? With local mixed modes, with local deflections, but in global mode 1, but fracture takes place in mixed mode propagation. The fracture angle measured theta, the macro angle, the fracture angle measured in relation to the cross section, also increases with plastic deformation with the drawing manufacturing process, producing fracture in this mode we could define as locally multi-axial fracture. And here the load displacement curve in 0 to 4 steps of cold drawing, slightly drawn steels or hot roll material, not drawn at all, Mode 1 behavior was a linear plot, and we have a non-linear plot for heavily drawn steel, but it's not caused by plasticity. In certain degree, yes, but it is very confined. It's low level of plasticity. The effect is, we define Fy and Fmax, and Fy is linked with the pop-in phenomenon. A pop-in produced by burst, by sudden tearing, by an isotropic tearing. This is when the embryo of crack deflection appears here in By, and we obtain the pop-in, but we still have loading-bearing capacity of the wire. Then we define the maximum load, the limit of the linear behavior or elastic behavior, and the Fy, which is not plastic yielded by micro-tearing by an isotropic resource. This is crack splitting or delamination. This is the phenomenon. We have observed it by stopping the test and performing a fractometallographic analysis. An analysis of fractured pads or crack pads with metallographic polishing. We call it fractomaterialographic or fractometallographic analysis. And now we use the mathematical equations of the French school long time ago, Amestoy and others, I think. We use the local crack tip field, the local stress intensity factor, minor K1 and K2, and with a matrix as a function of the global, in the fracture mechanics sense, K1 and K2. We define the energy release rate as a function of the local K1 and 2 minor letters, and with this we have a directional J, a directional energy release rate, and on the opposite side we can retake the concept theoretical or mathematical, not physical, fracture toughness or pseudo toughness or critical stress intensity factor with directional properties. K1 theta as a function of the K1 in zero direction, in transverse direction. Yeah, this is the hypothesis of our group. This is not by Amestoy, sorry. We use the mathematical equation by Amestoy, but we produce this deflection towards 90 degrees. We neglect this small branch, the popping of crack delamination, the bonding, splitting. This splitting path parallel to the drawing direction, we neglect, and we consider the second branch, they are very small, the limit to zero of this angle, to obtain the directional toughness. Then, our approximation or assumption is we neglect this part, the popping, the splitting, and we consider just the branching, the deflection microangle for initiation of an isotropic fracture. With this consideration, we have two papers, Toribio and Pariente. One of them, the longer in engineering failure analysis, explaining this procedure on the basis of the Amestoy and co-worker equation. And with this, we will finally obtain the K1C, or critical stress intensity factor, because the concept of toughness with mixed mode propagation could be dubious. Really is a dimension with dimensions of K, but this is an energy release rate, directional. And we obtain this pseudo toughness in 0 degree and 90 degrees and for any degree. Then we obtain the following ideas interpreting this plot. A directional toughness or a directional critical stress intensity factor or a directional energy release rate which increases with the drawing process. The increase of critical stress intensity factor associated with the theta angle is much more pronounced than that of the 90-degree angle. Okay? Here we have a clear increase, but in 90 degrees we have the similar energies with independence of cold drawing for splitting or delamination. That's logical for the bonding. And finally, the discussion of this plot with regard to angles, a beautiful plot, the macro and micro. Perlite colonies and lamella, crack deflection. They really have the same trend. It's really a nice approach. Then we have the macro-micro relationship typical of material science. We are entering material science and leaving fracture mechanics. We can go to the restaurant. Macroscopic fracture angle theta and microscopic perlite lamella angle theta n, both measured relative to the wide cross-section, increase with plastic deformation, with similar trend of evolution. is really nice. And with regard to the toughness, we could define this pseudo toughness, directional toughness, directional critical shift, directional energy release rate, K1C 0 degree, the transverse, increase markedly with plastic deformation. Then the higher the yield strength, the higher the plastic, the cumulative plastic strain, the more intense the cold drawing, the higher the toughness, the transverse toughness. Then cold drawing not only improves the yield strength, the classical resistance, but also the fracture toughness in transverse direction. But the problem is this splitting, this crack, the branching, this the bonding of the lamination, because while one K1C 90 degrees is only slightly increased, it's almost constant, very rarely speaking. There is no improvement with regard to the bonding or the lamination. That's sad, but that's what happens. For high deformation, K1C 90 degree is significantly lower. This is the weakest phenomenon than K1C 0. That's the problem with pre-stressing steel. This is an isotropic fracture. And now let's go to the conclusion. The chairman is standing up, but we finish. Cold drawing in perlitic steel induced strength anisotropy associated with a deflection angle. This is the bonding, the lamination in the crack path, the conference crack path, changing from being transversal to the Y to producing crack deflection with an ever increasing angle as the degree of cold drawing increases during manufacturing. The directional toughness or directional critical stress intensity factor, IR, or directional energy release rate, depends on the microscopic deflection angle of the fracture crack path. That angle being in turn a function of the microstructural orientation angle of the perlite lamella, as a consequence of the microstructural orientation induced itself by manufacturing process by cold drawing. Then cold drawing is beneficial. We know long time ago it increases the yield strength. This is the final point of manufacturing. But in addition, manufacturers don't know, they are not aware. But in addition, improves the fracture behavior in mode 1 and the fracture toughness, the classical for transverse zero angle in perlitic steel, by increasing the fracture toughness. But it induced a marked anisotropy in its fracture behavior, a strength anisotropy, due to the strong microstructural orientation. The strong microstructural anisotropy. And that's all. Thank you very much for your attention.